So now we continue with identification somehow. Now we hear something of application of identification codes to the two-party privacy preserving record linkage. And the talk is presented by Linkage-Yangling Chen. She is from Volkswagen Infotainment GmbH in Bochum, Germany, and she will tell us what is her idea to use identification codes.
Yeah, first, thanks, Christian, for the invitation. Actually, I was positively surprised, and I would like to share this topic really with the audience. This topic, actually, I did, this is before I joined the company, and in my previous project, when I was still with the University Duisburg-Essen, this is actually an interdisciplinary project. You see that I actually get touch with identification code actually through this project when I was working on the privacy preserving record linkage problem. So, okay. The outline of my talk. So first I will explain the problem. Actually, it's quite easy. I mean, I suppose every person here, you can get this immediately. And also the observation of this record linkage problem that can be reformulated by the identification over channels. Then the attempt is to apply this identification code to this specific problem. And I will show you also some numerical result, and I will conclude at the end. What's the record linkage? So the record linkage itself, it's a very old topic. You can see that it first described by Dun in 1946 as a book of life for each individual. So basically, we have all data saved almost in different institutions with your name, first name, last name, and other metadata and year of birth. And these are all personal data, and in nowadays, we are also producing personal data even more and more. So because we are in the era of the big data. So the record linkage problem basically is a process of identifying and linking records that corresponding to the same individual, but among different data sets. So for the people who has been working on similar problems, this record linkage, this terminology could have a different name, for example, data matching, entity resolution. And also if you work on the same data set, this technique is called also duplication, deduplication or duplicate detection. This basically itself is already a challenge topic. There's some factors, for example, when it deals with personal data, and we don't have, let's say, it's difficult among different data sets to have a common identifier. So basically, you don't use one unique, but several quasi identifiers. And these quasi identifiers mostly are these attributes available, commonly available in different data sets. It could be names, could be addresses, telephone number, date of birth, and such as. But we know that those data can easily have errors because people may change their name. And also this name can be misspelled. My experience, I worked in different institutions and university, and almost in every place I have stayed, and my name was wrongly spelled, even in the official document. So you really have to inform them and to correct, otherwise, but it's you. So the thing is that even such things happens, and you still supposed to be able to match the records that's actually belong to the same individual. Especially in recent years, there are privacy regulations. I just list two, one from US and one from the European Union. And from the European Union, basically, it's the general data protection. So this can be found. It's available actually from the website. I have the link in the reference. But there, basically, it's required to protect the privacy, but what kind of protective measures you should apply, and also how to, it's also required that you should offer or guarantee a certain level of security, but also, again, what kind of security strengths you should reach, it's not clearly defined. It's a regulation. And so basically here I give an example is like if you want to conduct a scientific study, for example, finding correlation between certain kind of automobile accident and also resulting injuries, you might need data from the police record, from the insurance company and the hospitals. And you need those institutions share data and cooperate. And you get, then you could do the research, for example. And this actually the regulation require that those data, when those data need to be shared between institutions and the strong security, privacy has to be guaranteed. And mostly the best case is that if the data are anonymized. So it means you give out the data, but it shouldn't be able to link only from the data given out to link the specific individual. So that's the requirement. Here I give a general framework of this problem. So suppose we have a data set A and B, and we will see that it's very usual that the data will be kind of cleaned or pre-processing will be done, and we can suppose that we have kind of identifier or quasi identifiers to match. And basically, the part what we are caring about is this private index and this private comparison. So basically, the matching part. Imagine that this could be, there are two forms, often these two forms considered. The one form is that if there's a trusted third party, which is called linkage unit, is involved or not. So if not, we have a two-party protocol. So basically, you process your data, you anonymize your data, you send to another party. Another party will try to do the match. And the same for the another way around. But if there's a trusted party, third party involved, then basically the both data set owner will anonymize the data set and send to the linkage unit. The linkage unit will do the matching. This is supposed to be the private matching because he only sees the anonymized data and returns the result. So it just shows, okay, there are records, the linked records that were considered as matches. The mismatches for the linkage unit and also for the data owner A and B, it shouldn't be able to trace back to the plain text of the record. Then you will see if basically you have two data sets and each data set have a list of records. They may consist of the records belong to some individual. This actually appear in both data sets. And when for the linkage unit, or when you do the private comparison, basically you compare each anonymized record from A and from B, and you decide if it's a match or not. So immediately you see for each comparison, it's an identification problem because it's at the end you have to answer, okay, is this record is a match to the record I have? Yes or no? Then you go to the next record. You will again to try to answer the same question. Is the record I receive or I compare is the one I have? Yes or no? So basically for two data sets, you will see that the comparison you need to be done. It's basically the production of the data sets A and the data sets B. And this, based on this reformulation, I mean, we actually expect we could apply our result in the edification for the edification problem to the record linkage problem. Yeah. So let's first look at the record linkage problem, how they measure, for example, how they measure the performance and how they measure the privacy. This, I think this is already explained in the morning's talk, and we know that in the field of record linkage, I mean, if you read the paper from that field, and you won't see that the error rate of type 1 or type 2, but you will see that 2 positive, 2 negative, false positive, and false negative. And even this what you hear is that the recall accuracy, precision, and specificity. So they have a different terminology, but at the end, it's the same. So basically, the arrow here, it's just the false negative and false positive, and what from the information theory, what we consider, we call them like a type 1 or type 2. And also for the linkage problem, we consider the transmission channel is noiseless. So basically, you don't consider this type 1 problem error anymore. We just focus on the type 2 problem. But just keep in mind, they have a different terminology in the applications, but basically they are the same. So we can write like differently information theoretic perspective of these probabilities, the rates. And for the privacy, actually, there are no commonly accepted privacy measures. If we could also, I could go more detail in this part later. Just for comparison for the education, of course, you already know that we consider the lambda 1, lambda 2 corresponds to these type 1 and type 2 errors. And also for the, so this we could actually prove because the definition, we can get their relation, the relation between the precision, recall, and specificity. So those terminology and meet the relationship to the lambda 1, lambda 2 error rate, what we consider often in the information theory. So that we can easily see that if we have this, make this 2, lambda 1, lambda 2 error rate very low, then we also get very good performance in precision, recall, and specificity, and for the record linkage. And for privacy, of course, we could use the information gain, and this could be quantified or upbounded if we assume that the records are uniformly distributed, for example. Of course, based on some assumptions. So then let's go a little bit more into the detail. So now we see that these two problems has so many similarity, and basically we can use this is our wish. We see similar problem, similar formulation, and we have nice result and construction in one theory, and we may apply this to another field. And that's actually where I start to look at the paper from the identification code, and I really want to find a net code that I can use and to prove that it really do a good job there, and it's a good fit for the application. So this is actually a very well-known result from Voodoo and V. So this construction of this identification code could be done via a concatenation of the transmission code and a binary constant weight code. And here, since we are considering noiseless channel, so we can forget the transmission code is basically a representation of the identifier or the message. And we just need to focus on the construction of the binary constant weight code. Yeah. If we check again the construction of this binary constant weight code, we see already also from Bordeaux and Weiss paper, they already mentioned the explicit construction on this, basically based on the concatenation of the PPM code and also with the error correcting code. So I think in the talk from the in the morning, I think basically they used this construction. But there is also another construction was proposed by Kurosawa, Yoshita. So they are using this Epsilon almost strongly universal class of these hash functions. And they are, so basically this kind of special class of a hash functions, it already corresponds to a binary constant with code. And there's also, again, construction, if you compose it with an error correcting code, you again construct a new class of these hash functions. And this is again corresponds to a new binary constant with code. So these are the constructions available. If we go, actually this, I see, since Christian has sent me a list of papers, this already observed that they are basically the same thing. You see that the first initiation of this PPM code or almost strongly universal class of hash functions, they are also they both are also the binary constant bit code. And then you combine with another 1 level, 2 level error correcting code, you create new codes based on that. The idea basically the same, and to send a pair of this challenge and tag pair. You see often from the information show, it's often discussed the construction of the code optimum for identification. So they have some vectors, the weight vector and the second order rate, and also overlap fraction. And you will see that if the converges to, they satisfy these conditions, then it's called that they are optimal for identification. But for the application, we don't need that they are so optimal. Let's see, we actually have other concerns in the application. Basically, the concrete code, that time I was considering it's, I focus mainly on the construction based on the ASU class of hash functions. And here I show you the structure, the construction, so which is proposed by Dimbo. And this incidence matrix gives a binary constant with code. Actually, I think I can show you here also. You will, the first column from 1 until the, so this until the cardinality of the input output, you could consider as these are the messages. So these are the number of the messages. You count from 1 until this, so many messages you can use the code. It's also the number of the messages can be identified by the ID code constructed. And each row, you have you have so many, you have exactly Q1s. So to satisfy this, basically this column. So the one is it's 0 if this function doesn't hold. It's 1 if the function doesn't hold. So for each message, there will be exactly like Q. This is constant weight. So those the ones the equation holds it's Q. So it's the same for each row, and for each column, it's actually reflected by the overlap because you have the overlap factor, and overlap factor, and it shows the rate of collisions. Yeah. Another construction is still based on this one I mentioned here, but I didn't do this in the simulation because you see this is already combined with the error correcting code. And here in the example, I actually take a read zoom code, but I will show you the difficulty of implementation of this one. So from the information theoretical perspective, we can easily give some upper bounds. For example, on the identification capacity, on the transmission cost, on the randomness for the anonymization, which is basically the part we used for the challenge, and also this probability of missed identification, because this one is just noiseless, so lambda 1 is 0, and probability of false identification. And also the information gain. So the information gain, so it's upper bounded if we assume a uniform distribution of this message set. Actually, in the reality, it's not really the case, but it's just to give some ideas. And especially the relative information gain, it probably make more sense. Yeah, but we will see that we can tune the parameters, the parameter Q, the parameter K. Then we will see that especially the false identification, because we really want to make it small to guarantee a good performance. And for privacy by the information gain, we somehow could have an argument, because this is a challenge tag method. And we could guarantee actually from the anonymized, from the information you receive, basically you cannot treat back the, you narrow down, but you don't trace back to the record. Okay. So this is in the, if we have the encoding decoding in our algorithm, you will see that it's really pretty easy. Basically, you have the message representation of the message A and alpha, and you choose randomly E1 and you calculate E0 and fulfill this function, and you send the pair which E1 is the challenge and E0 is the tag. And for the decoding part or the linkage part, you have already your message. And you will have a representation, and you get the challenge tag, pair E0 and E1, and you check actually if the equation is fulfilled or not. So you get immediately a yes/no answer. So this one is based on this simple construction of this almost strongly universal hash functions. So this is very fast. So computational point of view, it's very good. So this is a code 2. If we introduce the rhizomal code into the construction, and then we have an extra step. We have an extra step in both encoding and decoding. We have to calculate the code words in the rhizomal code, which is over an extended field, and to have it represent as a vector in the prime field. From the decoding part, the same. So basically, this step is very costly, and also we have to write the library ourselves. I think in most, software to implement this. Okay, some numerical result. Here, just some facts. So the data actually takes from the data set was sampled or taken from the North California, California Water Registration Database, which is also online available. And simply just consider the first name, last name, maybe also other attributes like age or year of birth or something like that. And sampling size for the data set A and B, basically from 5,000 to 2,500. So, and the coding methods, I just consider like a plain text, because this is just used for a simple comparison or just a hash, or this identification code C1. And the programming language is, it's used, this implementation was done in R, yeah. Okay, so here it shows some linkage quality. This MPR, basically it's the mean of the processing and recall. And you will see that for the identification code 1, we can tune the parameter Q and key. And we will see, for example, if you increase Q, you see from the different color that, especially the green color, you see the top, which shows the top quality also, and for the largest Q. But if you increase key, it doesn't mean necessarily that you increase the performance, because we know that the key plays a role in the false identification. And another factor we are carrying is that it's of concern is basically the timing. So how much time it costs for the anonymization, for example. Basically, this anonymization can be done separately before you send the dataset out. But this, you will see that for the AD code, if we increase the file size, actually it's increased quite quickly, the timing. So the timing is, for the plain text is quite stable. You actually don't need to do any, it's just for comparison. You don't need to do any anonymization. For hashing, you see there is something, but basically it's much lower than the AD code. AD code you see for one file size, there are different points because I tuned the parameters a little bit. So basically you get a overall idea, so how much time it may take. But so from the timing point of view, it's more timing costly. And also for the linkage. For the linkage, we could also see that the AD code is much more time costly than the hash and the plain text comparison. Actually, the reason here is that for the hash, you could do like a pre-computation. So basically, you prepare already the hash before comparison. But for the AD code, we have this challenge part. You cannot prepare. You only get it. You have to take what you have and you do a comparison. So there's no pre-computation was taken for the AD code. So basically, we see here in the figure, it's more time costly. But actually, I didn't show the figure. If we don't do the pre-computation computation for the hash, actually this AD code C1 could be better. It's actually very close, so even can be better. Okay, I will come to the conclusion. So basically, the identification, we also had some discussion with the colleagues here. Identification code, especially this construction we use for the numerical result, it's quite similar to the hash, but it's a special kind of hash functions, let's say. But these special kind of hash functions give a objective evaluation of this linkage quality and also privacy, which I think from this point of view, it's an advantage of using this method. But there are some open problems. The open problem is that here, basically, we are using like exact matching. So this scheme is not error tolerant. We don't tolerate any errors. So that's actually the part. This scheme works fine if the data set is clean. You don't have errors. But if there's errors, it's actually we have to consider multiple match key or multiple identifier and combine like you have all all operation for the method or multiple AD code. And also this attack model, because in the privacy domain, we have always to assume they are publicly available data sets. This is different from the information theory kind of security model. But I want to show you here this this part. So I mentioned the attack model here. So the attacker could have access to a global data sets. The reason is that what we are using for the numerical result, there's a publicly available data set. You can use it to analyze if your scheme is good or not, but also the attacker could use it for the re-identification. And we could assume that the attacker get encoded data set, and also this the worst case that is that the encoded data set contains the record of the individuals is actually subset of the global available data set, and the worst case they are the same. Yeah. So there are also other privacy measures was mentioned or was studied. So it's quite different from the information gain. So that's why I just listed here for the information. Yeah, I think that's all. If you have any more questions. Okay.
We can go to the file sizes and the graph that you showed for the linkage time. Yes, maybe what's the units here?
The unit is minute.
But for the file sizes, how big? Like in what unit is the file size in?
Unit for file size?
Yes.
This number of records for each number of records for each data set. So it's similar. So which means here you are doing how many comparisons you are doing 500 times 500, right? It's a square.
Mm-hmm.
Yeah, because you have to compare each pair. And here you're also again square, basically. The comparison you are doing is actually the square of the data sets.
Okay, it's here.
This is published, numerical results were published. Thanks for Christian. Actually, I didn't know it was available online, and he found it. Yeah.
So you can identification also have the advantage that you can pre-share what you call challenge or this randomness.
You mean pre-share the randomness, then they can also that's actually a good idea. So then it means that I do have another figure if there's a computation, right? Yes, it's actually different comparison. I should run the simulation again. Yeah, thank you.
Okay, then thank you again.